Great. Okay, it's 3 minutes after the hour, so I think we can go ahead and get started. My name is Jeremy Gregory, and I'm the Executive Director of the Concrete Sustainability Hub and one of the principal investigators who's involved in research at the Concrete Sustainability Hub. And what I'm going to talk to you today is about our research related to sustainable pavements. And this is work that's sort of evolved in the hub over the past 10 years or so, and it's accumulation of a lot of what we've done. And I think the basic premise of this research is kind of asking what seems like a basic question, but it is, what is a sustainable pavement? And this is certainly something that we see a lot of people try and answer, and certainly you hear a lot about this. There's a great guide that the National Concrete Pavement Technology Center put out several years ago about what are sustainable concrete pavements, and the National Asphalt Paving Association also has a lot of information about what makes for sustainable asphalt pavements. But at least, I think a lot of the discussion about sustainable pavements usually focuses on materials. And of course, that makes sense because that's literally what a pavement is. It's made out of those materials. And so that makes sense. However, what you've seen the discussion shift to, and certainly what our research has done in the hub as well, is that, more of a life cycle perspective should be used to quantify these environmental impacts. And that is because if you think about it, the pavement, of course, has these materials, and anything we can do to lower the environmental impacts associated with those materials will help. But there's also ways that we can use design and construction to lower environmental impacts as well. That is, if we can design a pavement to use less material, that can lower environmental impacts. If we can create longer lasting designs, that can also help. But there's an element of the pavement that we also call the use phase that goes beyond just the materials themselves. As you'll see today, the way we design and maintain our pavements affects the fuel consumption of the vehicles that drive on them. Also, any way that the reflectivity of the pavements affects the urban heat island effect. So those are elements of the materials that have other impacts on the environment around them. And of course, anything we can do to enable material recovery at end of life is also going to help. But we really need to take that full life cycle perspective to assess, what we mean by a sustainable pavement. Now, the main methodology that we use to quantify those life cycle environmental impacts is called life cycle assessment. And the way that it works is we basically break up all of these different life cycle phases into individual processes. And then within each process, what we do is we quantify both energy flows and raw material flows going in, and then also releases to air, land, and water, okay? And we sum that up across all of these different processes to get the environmental impact. So, for example, when someone talks about a carbon footprint across all these different processes, what they're tracking are emissions to air associated with greenhouse gas effect, right? But we could also look at toxicity-related emissions to air, land, and water and track those. Sometimes people just track energy consumption or raw materials. So there are many different metrics that you can use. But of course, the one we hear the most about is emissions associated with climate change. And sometimes that's called global warming potential or greenhouse gases or carbon footprint, but they all basically are primarily about that. And that's mostly what we'll be talking about today, even though we can calculate other things. Now, the Federal Highway Administration has a Sustainable Pavements Technical Working Group that's published quite a bit on this. A few years ago, they published an extensive life cycle assessment framework that gets into a lot of details in terms of how you do that. And the great thing is that this has started a discussion within some departments of transportation about evaluating pavement life cycle assessment. But at least right now, the vast majority of DOTs are not really using it to support design decisions. So there's kind of a gap there. The other thing that you may have heard of are environmental product declarations, and these are basically reports, in this case on paving materials, on the environmental impacts of those paving materials. So the National Ready Mix Concrete Association has a program where they report EPDs, and so does the National Asphalt Paving Association has a similar program, and these are great. But one thing to keep in mind, these EPDs are basically life cycle assessments of just producing the paving materials. They're not a whole life pavement LCA. So they can help when you're making often what I call vendor decisions, perhaps in trying to compare different vendors producing the same thing if they're done in a consistent way. But it's not, you can't just say, oh, this is a sustainable paving material just based on the EPD by itself. So what this leads us to is that there's a couple different challenges that we see when it comes to this whole field of, pavement sustainability. One is I think there are real misconceptions about what it means to have a sustainable pavement, right? As I mentioned, you talk to a lot of people and they say, oh, I use recycled content, that's a sustainable pavement. And as you'll see today, it's about a lot more than just them. The other thing is that right now, Pavement LCA is not really supporting design decisions, right? So when it comes to actually designing sustainable pavements, that process is not being used. I think the other thing that people have a hard time grasping is how does context affect the life cycle assessment results? And this will be a big theme today, but by context, I mean, what's the location? What's the pavement design? What's the materials and rehabilitation schedule? All the things that craft sort of a specific scenario. And people have a hard time kind of understanding how different contexts are going to affect those results. And lastly, there's just no question that there's uncertainty in this whole process. There's uncertainty in data, but there's also uncertainty based on the fact we're trying to predict something that's going to happen decades in the future, right? And so some people wonder, well, is it even worth doing that? So that can lead to some real questions about credibility. So those are all different challenges, and we've tried to frame the research that we're doing in the Concrete Sustainability Hub to address each one of these. So first of all, you'll see I'm going to talk about what's the importance of taking that life cycle perspective and framing what we mean by sustainability. The other thing is we see a real opportunity to integrate this life cycle assessment into the pavement design process. And then the other thing that we've done is tried to conduct life cycle assessments for a wide range of different scenarios to try to understand that impact of context. And then lastly, rather than be afraid of uncertainty, we try and really embrace it to see how we can create more robust outcomes. And by robust, I mean that we can have confidence in the outcomes in spite of the fact that there's uncertainty. So the life cycle assessment model that we use includes all the life cycle phases of the pavement. So starting with materials, extracting those materials out of the ground, creating them to make a paving material, transporting them to a construction site, the equipment that's needed to do pavement construction. And then once it's created, then there's different elements of both the use phase that I'll talk about, but also maintenance that happens in the future. What are the materials and the construction associated with that? And then lastly, we call it end of life, but of course, usually that means some kind of major rehabilitation or reconstruction. So what's the elements associated with that? Excavation, landfilling, recycling, transportation. A key thing to note, as I said, is that we call it a probabilistic life cycle assessment model means that we include uncertainty in environmental impacts, the quantities of materials that are used, the deterioration in the pavement that happens in the future, and also the excess fuel consumption that occurs. So we'll see how rather than using just a single number, we use a distribution of numbers in our inputs, and that also gives us then a distribution on the output. So a lot of what I'll show today is actually, just to kind of simplify things, a lot of median or or mean average results, but you'll also see how we can use uncertainty to support decisions. Now, what I want to dive into a little bit is what are some of these different use phase elements here. So one of them relates to pavement albedo, which is the reflectivity of the surface. Another one is related to lighting, which is also about the reflectivity of the surface. So lighter pavements require less lighting fixtures if those are going to be used. Another element is carbonation, and this specifically relates to concrete and how it absorbs carbon dioxide over time. And then the last one is related to pavement-vehicle interaction. And what I want to do is dive into a bit more what are the more complicated ones, which are the albedo and the pavement-vehicle interaction. Let me start first with the albedo mechanisms. There's a couple of different elements that we're accounting for in our models. So one, when we have incoming radiation from the sun, we quantify a few different things that are related to that pavement reflectivity, or albedo, which ranges from 0 to 1, 0 being perfectly dark and 1 being perfectly reflective. So there's a couple things. Is that one thing is that the air temperature cools. If you increase that pavement albedo, that cools the air temperature, and that affects the energy consumption of buildings that are nearby. So obviously this only matters if you're in an urban area where that can be affected. Okay, so there is a cooling effect, and obviously that can actually increase heating requirements in the winter and decrease cooling requirements in the summer. But there's also incident radiation that goes directly into the building. And this kind of has the opposite effect. It increases cooling requirements in the summer and decreases heating requirements in the winter. Lastly, just the reflectivity of any surface on the Earth affects the amount of radiation that's going back and forth, and that's literally creating this greenhouse effect. And so that radiative forcing is also captured in our models. And once again, if you increase the albedo of the pavement, it leads to what we call a cooling effect as well. So we have to balance all of those things, and that's going to depend on the climate and the building configuration. The other elements that I wanted to talk about are related to pavement-vehicle interaction, and there's a couple different mechanisms that we're tracking. One is based on surface roughness, and basically a vehicle driving on a rough pavement is consuming more fuel than one driving on a smooth pavement. And we call that difference the excess fuel consumption. That is, there's a certain amount of fuel required to move the vehicle forward. This is an additional amount associated with that energy dissipation. And so basically that's one form of pavement vehicle interaction that we're tracking. Another one is what we call deflection. And this really relates to very heavy vehicles, primarily like trucks. And basically, for depending on the stiffness of the pavement, the vehicle can create a deflection such that it's like the vehicle is continuously driving up a very shallow hill. And that also leads to excess fuel consumption compared to if it were driving on a perfectly rigid surface. So these are two different types of pavement vehicle interaction effects that we're tracking within that use phase. Now, I mentioned one of the gaps when it comes to the pavement design process is that, usually what happens in the pavement design process, we start with some initial pavement design, and then we analyze it using mechanistic empirical design principles. And that's really the basis of our typical design process. And then we get our final design. And what usually happens is that we look at, we generate the data and then do a life cycle assessment or a life cycle cost analysis after the design is finalized. So what we've been trying to do is basically develop a linkage between all these things so that we can actually iterate with these together to then determine that final design based on not only just the performance of the pavement design, but also what are costs and environmental impacts. So I think that's a real opportunity that we see that we're trying to do. The other thing that we've done is we've conducted life cycle assessments for a wide range of contexts. And as you can see here, we had a pavement design firm, Applied Research Associates, come up with pavement designs in 4 different climates here. that represented a range of climates. And then also pavement designs for 3 different traffic levels, low, medium, and high. And then also several other different framing conditions. We looked at asphalt, concrete pavements, different types of maintenance schedules, design life, analysis periods. So what I'm going to do now is transition to telling you what are some of the key findings of our research in this life cycle assessment space. First of all, one of the key themes you'll see is that this life cycle perspective really matters. Okay. Number 2, we found that context matters. And as I mentioned, that context is really about location, pavement designs, treatment schedules, things like that. Pavement-vehicle interaction matters, albedo matters, and also there's significant opportunities to improve. Okay, so now I'm going to dive in and show you why we found each one of these. The first thing that's important is that life cycle perspective matters, right? When we look at basically at least the life cycle greenhouse gas emissions of pavements, then in many cases, the key drivers here, as you can see, are the use phase and materials and construction. And this is showing some analyses that we did. This is life cycle greenhouse gas emissions, the breakdown for urban interstate pavements in Missouri. And note that at the time that we did these analyses, we didn't really have sophisticated enough albedo models. So these do not include albedo right now. So the use phase includes that excess fuel consumption due to PVI and also lighting and carbonation. So the key thing that you see for these urban interstates, the use phase really drives, followed by materials and construction. And it's kind of interesting. Those are about the same for both the asphalt and the concrete pavement. Now, if we dive into this materials and construction phase, what you can see is that the drivers are really different depending on whether it's an asphalt or a concrete pavement. So, for example, in the concrete pavement, the cement is really what's the key environmental driver here for greenhouse gas emissions, whereas in asphalt, it's mostly the construction and the transportation. So the raw materials matter less there. Now, if we dive into that use phase component, you can see here that what's really driving it is the excess fuel consumption. And as I mentioned, albedo isn't included here, but the roughness and deflection, though, the difference between the two is different among them. But in both cases, it makes up over 90% of the drivers of that use phase. Okay. Now let's look at a few different ways in which contexts matter. So one of the things you can see is that when we vary traffic levels, so these are all different types of concrete pavements in Missouri, what you see is that the more traffic that we have, and this is showing the average annual daily truck traffic increasing here, that really affects what those life cycle greenhouse gas emissions are. And part of it is that we're using different designs to handle those different levels of traffic. So the relative amount of materials and construction increases, but also the use phase really increases in that as well. The other thing that we see is that the impacts really vary with location. These are showing urban interstate asphalt pavements in 4 different locations. The materials and construction is different because the pavement designs are different, but also you can see the use phase is really different, and we'll unpack that in a little bit when we look at what's going on within there. But basically, the location can really affect the type of results that you're getting. Another thing that we found is that depending on the type of material and maintenance and rehabilitation activities that you're doing, that can affect life cycle results. This is showing a rural local highway concrete pavement in Missouri, and under this they follow a conventional maintenance and rehabilitation schedule where they do a single diamond grinding throughout its life. In this one, they've done an additional diamond grinding throughout its life. So that increased the maintenance and rehabilitation, but it decreased the impacts from the use phase for a really significant benefit throughout that. So even though that additional diamond grinding had an additional cost, it really lowered the overall life cycle greenhouse gas emissions. Now, the other thing that we can look at is how different pavement designs can affect life cycle greenhouse gas emissions. And what you can see here are the asphalt and concrete pavements in the 4 different climates. And you can see there are times when concrete is lower, there are times when asphalt is lower, and it's going to depend on that particular context. And at least what you can see for these urban interstate pavements, a lot of what's going on is that use phase. But you'll see that usually, like for example, in this Arizona and Florida, the concrete has a higher initial cost, but in those cases it has lower excess fuel consumption. And let's dive into that a little bit. If we just look at the use phase associated with those, what you can see is that there's quite a few differences when it comes to both roughness and deflection. So for example, in this case in Missouri, the roughness is really driving the impact of the concrete pavements, and that makes that higher. Whereas in the warmer climates, you see that deflection really dominates, in particular for Florida and Arizona. And that's because when it comes to the viscoelastic response of asphalt, higher temperatures really means that the deflection is a larger deal, whereas you don't see that nearly as much in Colorado and Missouri. Now what I want to shift to is actually looking at some cases where we have done some more recent modeling on related to albedo. So this is still that full life cycle impacts, but now we're looking at what are the GHG emissions associated with different decisions around the use of albedo. And what we've done is actually we've been able to get pretty, what I would call hyper-local contextual analyses. And this is really enabled through the use of GIS data. And what we can do, these are showing different census regions in the city of Boston. And we're able to extract different characteristics of the buildings that are in those regions. In particular, what are relative heights? What's the distance apart? How close are they to the roads? And what we can do is within those, then we can really look at individual pavements because we're able to pretty efficiently model the impact of the changing the albedo of the pavement within those regions. So there are many different ways you can increase pavement albedo. This chart right here is showing life cycle savings of replacing flexible with rigid pavements. And what you can see is this chart right here. So a positive saving means a positive number means just that it's a saving, whereas a negative number would mean it's actually a net burden. So generally you see a net positive associated with that. The other thing is that we calculate, if you're interested more in the urban heat island effect, we do show that increasing that pavement albedo does lower the maximum urban temperatures that we see. But let's dive into a few cases here so we can unpack a little bit what's going on. And you'll see once again how this context really matters. So this is an urban pavement in Boston. So high truck traffic. It's also in a high-rise, dense neighborhood. And when we look at the life cycle results right here, here's a few different types of cool or, sort of conventional and cool pavement designs. So this is a conventional flexible or asphalt pavement, and the alpha is the albedo, so 0.1, and that's usually like an average value for asphalt there, and a rigid or concrete pavement here with an average albedo value right there. And then we can make both reflective versions of asphalt pavements and rigid pavements using either coatings in the case of asphalt or different types of binders or aggregates in the case of concrete. So what we're showing here is that blue is materials and construction. This is roughness related. Dark orange is roughness related excess fuel consumption with International Roughness Index, and the lighter orange is deflection induced excess fuel consumption. So once again, you see from that life cycle perspective, on these urban interstates, then those are really what's key drivers. The green right here is actually, so that's albedo related to radiative forcing and albedo related to building energy demand. What you can see is that basically we see there's a slight burden right here when you have lower albedo, but then for the higher albedo, you actually get a net negative. And that's why this dot right here shows the net across all of them. So that's an urban interstate case where we see, in Boston, where we see some of these net benefits albedo. What's interesting, though, now if we look at a local road where we have much lower traffic, so we went from AADT of 71,000 to AADT of 600, right? And now we see very different. So we see that basically the blue right here, the materials and construction, is really dominating, and now we see PVI much less. And also what we see is now that the albedo can be as significant, if not more, than the PVI. So this really changes sort of that calculus of what really matters. And so this is why we come to this conclusion that albedo matters as well. Of course, it depends on context. It's going to matter more in these lower volume pavements, but it's certainly something that should be considered. And once again, that's for an individual segment of pavement. The reason we have different results over here is that there's so many different types of pavements in different neighborhoods. Now we're going to shift to a different city, and this is Phoenix. And now you can see there's different colors. There's some reds in here where actually that means that if you were to do this same kind of shift, you would actually get some where you would increase the burden. And now we're going to look at a couple different types of pavements. Once again, this is a collector, so sort of in between the two that we saw before, about almost 3,000 average annual daily traffic. And what you see here that's interesting is in Phoenix, at least, this dark green, the building energy demand is really much more significant. And in fact, it's a net burden. So that's why in this neighborhood here, you see so much red because of that incident radiation going into compact, closely packed buildings. You see that is a net burden. And so the reflective pavements actually are not particularly good right there. Whereas when you look at some of the other neighborhoods, in particular, this is the higher traffic neighborhood, which is an arterial. You see, 18,000 AADT, so bigger than this, not quite as much as the interstate, but still a lot of traffic. The PVI dominates more. And also what you see in here is that once again, for some of these neighborhoods, actually the building, you have to look at the net between that building energy demand. You do get a credit from the radiative forcing, but the building energy demand is not nearly as much. So once again, you can see how that life cycle perspective really matters. Now, one of the things I haven't really gotten to yet is how do we incorporate in this uncertainty? So even though we have probabilistic results for all of these, it's hard to show breakdowns of probabilistic results, which is why we show averages here. But it's still important to come back to that and talk about why uncertainty approach facilitates robust decisions, right? Because if we only look at both of these right here, it's hard to draw meaningful conclusions just from these two data points, right? So what we need to do is incorporate uncertainty to see, is the difference between these two statistically significant? It also can help us understand what are the drivers of the difference and what should we focus on. So like, for example, this is showing a difference between two results, and you can see there'd be like a median somewhere around here and somewhere around here. So you would think design C would have a lower impact, but what we really need to track also is correlation between these two. When we do different simulations, how much changes between them. And so we use a metric that I won't get into too much, but basically it allows us to say how frequently is design C lower than design A. And we can use some statistical criteria then to track basically what is exactly how frequently one is lower than the other. And so we can take that back to our now using a more statistical framework and basically ask this question, where should I use cool pavement designs, considering that there is uncertainty in those life cycle emissions? And so rather than just having it say, for example, should I use a flexible design, a rigid, a reflective rigid, or reflective flexible, now we come up with a few different options. And in cases where it says rigid or reflective rigid, what that means, for example, is that there was a statistical tie between those two, but they were still had a lower impact than the other two options. Whereas you can see in orange, there's 3 or more that are preferred, which would be rigid, reflective rigid, or flexible. In some cases where it's flexible or rigid. So this is a bit more of guidance now of ways in which, obviously, I realize not everyone wants to see all the statistics behind it, but this just basically tells us, at least when we account for that uncertainty, and then use a threshold to say what we consider to be statistically significant, we can then try and better then understand how that uncertainty would drive a decision. And as I said, even though there is uncertainty in it, we can still make robust decisions. What you can really see here in both these cases is that, sorry, this is Boston again and Phoenix, is that the location of the pavements and also the pavement designs, those are going to be some of the things that are really key drivers of what's the preferred alternative. All right, so kind of bringing this back to sort of what is sustainable pavement. I think hopefully now that these quantitative sustainability assessments, they really require this life cycle perspective. But what you also need to do is look at trade-offs, and we like to think about this in terms of trade-offs between performance, cost, and environmental impacts. And of course, what's tricky is that within each one of those, you can have trade-offs as well. So like, for example, within the performance, you may be looking at obviously meeting traffic loads, but maybe you're also interested in runoff or urban heat island effect. Within costs, there's initial construction costs, but there's also maintenance costs and user costs associated with delays from construction or the excess fuel consumption. And of course, within environmental impacts, there are different metrics: global warming potential, smog, ecotoxicity. So I'm not saying that this is easy, but it is important to frame them together, to analyze them together, and then to try to balance them. Now, one of the last points that I mentioned is that really large opportunities to improve exist. And I'm going to talk to you about a case of concrete pavements. In particular, this is important because, the average annual life cycle greenhouse gas emissions of all new concrete pavements in the U.S. is about 3.1 million metric tons. And one of the things that our team did was to look at what are the costs and also global warming potential reduction of different strategies associated with lowering the impact of concrete pavements. And this is how these are framed. There's a few different solutions here, and I'll get into those in a minute, but here's how you look at this. Basically, the width of each one of these is 100 million grams of CO2 equivalent reduction. So all of these strategies lower global warming potential compared to a conventional concrete pavement. The cost effectiveness, though, and we goes off an abatement cost, if it's a negative, that means the strategy saves money. Whereas if it's a positive, it costs money, but of course you're spending that money to lower the global warming potential. So there's a few different strategies that can be done. Using white aggregates, as I mentioned, that can lower impact associated with albedo, and extra rehabilitation. I also mentioned if you're doing that, you're keeping it smoother and lowering excess fuel consumption. Stockpiling concrete at end of life increases the amount of carbonation. That will lower impacts. Increasing use of fly ash will lower the impacts associated with the concrete. And this last one here is a case study that was done where basically the Mechanistic Empirical Pavement Design Guide, or MEPDG, a mechanistic empirical approach was used to optimize the pavement thickness. And basically, when they optimized it, they were able to make it thinner. Like a lot of pavements are over-designed for the cases in which they're applied. And so as a consequence, if you make it thinner, you basically use less material and also save money as well. So you're saving CO2 and money, so it's a clear win-win. And I think this is an important message that is particularly relevant for engineers, right? These are all things that we associate with sort of, traditional sustainability, but this is just kind of improving your engineering approach and taking a closer look at what you need for a particular design life. And I think that's a message that we also need to hear. The other thing that we did as a team is try and look at, what is the mitigation potential whole pavement network in the U.S. for lowering GHG emissions. And you may have seen this on a previous webinar, but some of our estimates show that basically there is significant potential to lower greenhouse gas emissions through some somewhat ambitious strategies associated with improving our pavement network. And what this chart is showing is basically, this is emissions, greenhouse gas emissions in the year 2016, which we use as a baseline, and these would be emissions in the year 2050 if we followed these different, what we call ambitious strategies. Now, some of them, we know that the fuel efficiency of vehicles will improve over time, and so we call that a projected action savings. And there is some increased use of recycled content in pavements already. So those are projected actions that are green. These orange ones here, though, are more ambitious, and a lot of them are dependent on investing more in our paving infrastructure. So that will then create smoother pavements. If we can make more use of concrete overlays, which are an efficient way to rehabilitate pavements, increasing pavement reflectivity, increasing pavement stiffness. What you can see is all of these things lead to cumulative reductions of 1.7 gigatons of CO2. And a reduction of 68% from 2016 levels, which is right in line with what the U.S. Target was in the Paris Accords. The other thing to kind of bring this back to the life cycle perspective is that you can see that whether it's 2016 or 2050, embodied emissions make up a much smaller fraction than those use phase emissions, right? So if we are really going to try and be ambitious about lowering GHG emissions, we need to take that full life cycle perspective. And as I mentioned on the previous slide, we absolutely should be trying to lower the impact of our materials. But if we can also design them smarter and design them so that they, lower vehicle fuel consumption and lower albedo-related emissions as well, we're going to get a lot more ambitious reductions. So just to summarize, once again, the key findings from our research: the life cycle perspective matters, context matters, PVI matters, and albedo matters. But we have some significant opportunities to make improvements. So just before I finish, I want to summarize what are some of the key target areas for reducing environmental impacts in pavements. Obviously, on the materials side, there are opportunities for both concrete and asphalt. Concrete, we can lower the burdens by increasing our use of supplementary cementitious materials, Portland limestone cements, any of those binders that kind of lower that burden associated with the cement. On asphalt, as we showed, the construction and transportation impacts really were driving that, but also increasing the use of recycled content can lower impact associated with both of those, and that's where reducing those transportation distances can also help, and using that recycled content also on site can really help. On the use phase, it's pretty simple: increasing pavement stiffness, decreasing pavement roughness, and increasing pavement reflectivity. Those are all the things that are going to really reduce those use phase burdens. Now, just moving back to kind of life cycle assessment and what are opportunities that we see to support pavement decisions in the design and construction phase. The decisions that are made can really benefit from this life cycle perspective. These are all kind of what if I use low impact materials, use of recycled content, increased durability, long life design, all of those things, any innovative techniques you're thinking of trying, what is the life cycle environmental impacts? Life cycle assessment should be used for that. And this is one of those things where I think trade-offs are important. For example, if you can increase the durability and hence, or the long life of the design, but you use what we call kind of low or high impact materials, it could be that in the life cycle of the pavement, that's a better choice. Now, obviously, we want low impact materials and long life designs, but if there are trade-offs there, we need to look at them in a life cycle perspective. I mentioned how maintenance and rehabilitation decisions can also benefit from this. If you're trying to engage more in pavement preservation that is more frequent but more minor treatments that extend the life of the pavement, you can look at that in a life cycle perspective. If you have new maintenance and rehabilitation activities, that can also help. Anything to minimize traffic delay can also be included here also. And lastly, asset management. If you're trying to figure out how to allocate funds or meet greenhouse gas targets, even at that large scale, there are ways that you can incorporate this life cycle perspective to help. And of course, if you combine these with life cycle cost analysis, then we call those eco-efficient solutions. Great. So that's all that I had to present today. We have a lot more information that's available on our website, and you can also contact us for further information here at CSHub at mit.edu. And now what I will do is turn to our Q&A section, and I can already see we have some questions that are coming in. So if you haven't, we have plenty of time, over 15 minutes to go through questions. So if you haven't, then please do. I see there's one that came in the chat, which I will answer that too. But as we said, please, we're looking more in the Q&A box, so you can ask them there. All right. First question, where can I see federal or state regulations enforcing greenhouse gas reduction in the construction industry, if there are any? And at least right now in the United States, we don't have regulation targeted specifically at the construction industry to lower greenhouse gas emissions. I would say with maybe one exception, and that is in the state of California. A few years ago, they passed what they call a Buy Clean legislation. So that's what you can look for, is California Buy Clean legislation, and that does target lowering the environmental impacts of some, I should say, of choose in the vendor selection for state projects of choosing vendors that have products with low greenhouse gas emissions. So that's relatively new. There are other states looking at that as well. But so far, we haven't seen anything that explicitly targets pavements. Great. So the next question is, on slide 21, are the concrete pavements in Missouri very rough on average compared to other concrete pavements? And this is a tricky thing. So the question is right here, so basically, and saying, Missouri can be relatively warm, and so a lot of these things are hard to predict. And basically, that was why we kind of left the pavement engineering to ARA to come up with those things. And all I can say is, to be honest, I don't have a really good sense of that, but it's also, we can get into data as to what the existing pavements is on average, but in these pavement designs, that's the deterioration models that they had for Missouri. Now, that's for these very specific designs, right? That's not to say you could make an asphalt design that was thicker and hence be stiffer and lower this. You could make some modifications to the concrete design to make it smoother. To me, I wouldn't read too much into these specific cases as generalizations for everything that can happen in Missouri. Rather, I would say that's what we found with these two designs, and there are opportunities certainly to improve both of them. Okay, there's a question. When you say flexible pavement versus rigid pavement to save greenhouse gas levels, do you mean replacing asphalt with OPC roads? So I presume that question is actually related to this next one here. What are the life cycle savings of replacing flexible with rigid pavement? So in that case, yes, the flexible refers to asphalt and rigid refers to concrete. And there's a couple of reasons that we look at this particular scenario. One is because there have been questions about, a lot of people talk about concrete pavements as cool pavements because they have a higher albedo. And so there are questions about, well, if you do that, doesn't that actually, even if that does lower temperatures like we showed here, doesn't that increase overall life cycle emissions? Because as we've seen, oftentimes the initial environmental emissions associated with construction are higher for concrete than they are for asphalt. And so, our point in looking at this is that if you are looking at that as a cool pavement solution, you need to really look at the full life cycle, not just the materials, but also the excess fuel consumption as well. And so we tried to look at that whole picture, and that's why we did it. The other thing is that in Boston, all the roads are asphalt. So if you're looking at that as a solution, then that's what makes the most sense. All right, another question. Let's see. Hold on a second, I lost track of where I was. What sort of materials are you using to create a reflective pavement? Are you increasing reflective aggregate, or is the coating that needs to be reapplied over time? And so we do have a couple different solutions. Usually the solution for asphalt that people are applying now and are testing in many different cities across the country is to use a reflective coating. And so it's literally like they're just painting the streets with this with a fairly reflective coating. In concrete, generally the solution just sort of by its nature, because the binder cement has a higher lighter color than asphalt, by its nature it's more reflective. But also you can use different kinds of binders. There are different SCMs that will have a higher reflectivity. You can use white cements, and then also you can use different reflectivity of aggregates in either one to both asphalt and concrete to increase the reflectivity. All right, have you seen an increase of Portland limestone cement with SCMs such as slag in pavements? And that's a great question. I know that my understanding, at least in the U.S., and I hope I can get someone else to chime in on this, is that Portland limestone cement is not being used that much in the U.S. in pavements. I don't really have a good answer as to why that is, because I know it is being used more in places like Canada and in Europe. So I think there are opportunities there, because with Portland limestone cement, you get basically the same performance and lower environmental impact. Now, having said that, there is use of SCMs in pavements, whether it be fly ash or slag, and that's going to be highly variable depending on the region. But those are definitely being used. Okay. Another question is about measurement of albedo, and how did you include the albedo in the sorry, I just went away. Let's see. How did you include the albedo in life cycle assessments? And did you use the models reported in the FHWA pavement LCA framework? This is a great question, and because as some of you may know, albedo is something that changes over time with pavement. So asphalt pavements usually start out dark and then lighten over time, and concrete pavements usually do the reverse. Start out light and then darken. The data that we've seen show that most of those processes occur pretty rapidly compared to the lifetime of the pavement. That is, within a year or two, they've sort of saturated to what the albedo is that they're going to be. And we did use data from some FHWA-sponsored studies to help us with that. The values that we use in our studies are considered aged, or what that sort of final is, and not the initial. All right, how do you foresee these insights being implemented when there is a dissociation between capital expenditures and operational expenditures? Paying for materials versus fuel savings from drivers. Are there straightforward ways to apply these insights into practice? This is a great question, and I would actually unpack it in a little bit different way. The capital, first of all, the question about capital expenditures and operational ones, with the capital expenditures being about that initial investment, either in that major, the initial construction or rehabilitation. those are usually separate funds from what I would say. There's also funds associated with maintenance and rehabilitation, and those are different within DOTs. And if you aren't doing the capital expenditures while thinking about how you minimize those other ones, and because those are different pots of money within the DOTs, then you're missing that opportunity. And that's why that life cycle perspective is important, and that's why it's great when DOTs are using at least life cycle cost analyses. Now, the separate issue about capital expenditures versus the operational expenditures of the drivers is also a really challenging one. And this is also one that we see in life cycle cost analyses, where there are defined procedures for calculating what's the user costs associated with sitting in traffic while there's construction. We also added on another user cost associated with this excess fuel consumption. Even though those can be quantified, it doesn't necessarily mean that transportation agencies are taking that into consideration. Rather, they usually are focusing on what we call agency costs, the ones that they're dealing with the most. And I understand that, but I think that it's also the duty of these transportation agencies to think about the expenditures of the users. And so it's part of the reason why we really communicate the importance of this life cycle perspective, to get people to understand that the way we design and maintain our pavements affect those. And so I think that's number one thing, is just to try to quantify those things and see how they relate, and then hopefully decision makers can start to see that importance. The other thing we can do, though, is have taxpayers start to bring this up as something that they think is important. So communicating to that audience is also important. All right, there's a question about the carbon app that we have, and was it used to determine roughness? And for those of you who may not be familiar, we do have an app that we've developed that can be used in your phone, and you just turn it on in your phone, and it measures the roughness of pavements, and then can then be used to help us paint a picture of what is the condition of pavements all over the country and all over the world. And so the short answer is we did not. In the cases that we first looked at, they were more designs where what we did is what was more important for us was to get a deterioration model. That is a model of when we create a new pavement, how is the roughness going to evolve over time? So that was kind of what I alluded to was going on there in Missouri. We had a deterioration model that was based on that. Now, those deterioration models are usually based on empirical data, some mechanical components and some empirical component. And the challenge is that empirical data, usually DOTs might measure roughness on pavements once a year, oftentimes every other year. So it's hard to get a good deterioration model based on data with so infrequent measurements. And so that was a big motivation for us to develop carbon, was to actually be able to get more frequent measurements so that we can have a better idea of what that deterioration is, because that deterioration is what's really going to affect this excess fuel consumption of roughness. So the short answer is not yet, but we would really like to be able to use carbon data exactly so that we can better connect it back into these life cycle assessments. There's a question about were the roughness values reported for optimized designs, and I would say that when it comes to the pavements that ARA did, yes, those were very much optimized. The case study that I showed before, let's see, with this one right here was a case where we took a location where we felt like it was not an optimized design. And I think there's still a lot of those cases throughout the country where agencies are sort of using the same design that they've always used. And so in the cases we looked at, yes, we feel like they were, because we specifically asked agencies to do that. But we still wanted to bring this up because we feel like it's a big opportunity. I also got a note from someone, Angela Folkstead in Colorado, who knows this much better than I do, that they are using quite a bit of Portland limestone cement and pavement. So thank you very much. I did not know that, but to answer that earlier question, it sounds like that is being used in at least one place. So that's great. All right, and the last question we have here right now is this presentation recorded and available later to view on your website? And the answer is yes. We are recording this, and we have a YouTube channel, and following this, we will post this to the YouTube channel so you can watch it or share it with folks who weren't able to join us today. And I think that's all the questions we have right now. I just got one other comment saying that PLC are approved by DOTs in a number of states, and so that is great to know. I was only aware of a couple where they weren't still using it, so there clearly are opportunities where it's approved. I think there's another question about whether or not they're actually using it. So. All right, there is a question about whether the PVI model considers traffic loading and pavement temperature as a function of time of day. And what we do is that we've done quite a bit of studies to look at sort of how much resolution we need on that traffic loading and the pavement temperature, right? Because we know that obviously pavement temperature fluctuates during the day, as does traffic loading. And because it's a viscoelastic material, the traffic loading will also affect the amount of excess fuel consumption that we get. And what we found is that although we can calculate those things, hourly, there's a lot of, weigh and motion data that's available. It really wasn't necessary and didn't affect our results much. So I believe that what we're generally using now is more monthly averages for temperatures, and because they gave us basically the same results as if we did daily or hourly. Great. There's a question about disposal. Do coatings affect recycling? And that's an excellent question that I had not considered when I presume this is about asphalt pavements and the coatings that go on. Do they affect recycling? And I don't know the answer to that, but it's a really good one. Great. And there's another question about do you have a single publication of the details of the work that's presented today? And we don't, and the reason is because it really has taken place over the course of a decade. But what we do have is on our website, there's CSHub.mit.edu and then /pavements, and then within the pavement section, there will be specific elements that are related to this life cycle assessment. And so that's a good place to find everything that, or at least support for most of what we've shown today. And if you can't find it, you can contact us and we can put you in touch with the more recent research. So. Great, and we're back to the top of the hour. I really appreciate everyone's questions and for participating here. We hope you continue to join us for these webinars. They're a great way for us to learn about what's important for you and for us to get the word out about our work. And so keep up the discussion. You can find us on social media as well, Twitter, LinkedIn, Facebook, all those things. And we hope to see you again on a future webinar. Bye-bye.